Okay, thank you very much, Angelo. So today's seminar is devoted to general reduced order modeling of turbulent and steady flows. Sorry, it's okay. And well, it is formed by 4 talks. Okay, 2 by senior researchers and 2 by young researchers. All 4 belong to several teams participating into the ARIA project. Okay, so let me introduce the first speaker. This is Samuele Rubino. Samuele Rubino is assistant professor at the Department of Differential Equations and Numerical Analysis at the University of Seville, and is also a collaborator member of the Institute of Mathematics. He obtained his PhD in mathematics in 2014 from the University of Seville and won the award for the best PhD thesis on computational methods in applied sciences and engineering from the Spanish Society for Applied Mathematics. Later, he had a postdoc fellowship at the Fondation des Sciences Mathématiques de Paris in 2015, affiliated to the Laboratoire Jacques Lilians, and he was postdoc fellow of Initiative d'Excellence de l'Université de Bordeaux in 2016, affiliated to the Institute of Mechanics and Engineering. In 2017, he won a contract of the Spanish State Research Agency and came back to the University of Seville, and where he is at present. His research mainly focused on numerical analysis of stabilized and turbulent models in fluid mechanics, with a particular focus on reduced order modeling. His talk deals with the treatment of instabilities due to advection-dominated flows with POD discretizations. Okay, somehow.
Okay.
Okay, thank you very much, Samuele.
Thank you, Thomas, for the nice introduction. So I'm going to share the screen. Okay. Okay, so good afternoon, everyone, and thanks for the opportunity of giving this talk, which aims to resume a part of my recent work at University of Seville in collaboration with Professor Thomas Chacon and Mehdi Assayas from Polytechnic Institute of Bordeaux in the framework of ARIA project. So my intention here is to present some results on the derivation and practical performances of a stabilized POD reduced order model applied to strongly advection-dominated advection-diffusion-reaction equations. So first we introduce the model problem and its continuous variational formulation. Then we consider the POD methodology, and we derive a streamlined derivative projection-based stabilization for the POD ROM. And we further improve this stabilization technique by an a posteriori stabilization, which is applied in the ROM framework, but both for the offline phase and the online phase. So in the offline phase, the reason is to limit the influence of noisy data in the POD snapshot creation, and in the online phase, the reason is to obtain more accurate and stable reduced order results. So finally, we apply this global strategy to numerical simulation of relevant test cases on relatively coarse grids by focusing on 2D rotating cylinder and traveling wave problems with very low diffusion coefficients. So we initially consider an initial boundary value problem for the advection-diffusion-reaction equation for simplicity of presentation. We just impose homogeneous Dirichlet condition on the wall boundary. So this is the mathematical form of the problem, where B is the advection field, nu is the diffusion parameter, G the reaction term, F the forcing term, and U0 the initial condition. So we are going to consider the variational form of this problem. So we introduce X as a continuous solution space, and here we have the weak form of the problem. So first of all, I spend some words on the full order model that we are going to apply. So we rely on a finite element approximation so that we consider a suitable finite element space, and we apply the standard Galerkin finite element method. So by simply doing that, we arrive we have the standard Galerkin FEM, but we know that for very low diffusion coefficient, this method is generally unstable, and it produces strong spurious or global strong spurious oscillation. So in order to overcome this problem, we are going to propose a stabilization procedure by interpolation, that is by considering an interpolation technique, in order to control offline the high frequencies component of the advection derivative. This strategy has been originally proposed in this paper, and for the Osin equation, and we use it in order to produce the snapshot. So and it may be cast in the local projection stabilization framework. So in order to briefly describe it, we consider that the finite element space is formed by continuous Lagrange polynomial of degree n. Then we define the tau scalar product and its associated norm in this way, and where tau k is actually a local positive stabilization parameter. And we arrive at the local projection stabilization by interpolation method, which is described here, where actually pH prime is the so-called fluctuation operator, and pH is an interpolation operator onto a projection space dH, which is formed by lower continuous Lagrange polynomial. So actually, in practical implementation, we consider pH as a Scott's sign like interpolation operator, and know that this interpolation structure is much cheaper with respect to classical LPS method, which instead use a local L2 projection operator. So we now pass to describe the reduced order model that we are going to consider. So we introduce the POD space, and by simply projecting by the Galerkin projection the corresponding equation onto this POD space, we arrive at the so-called standard Galerkin POD ROM. But again, despite its computational efficiency, we know that it has been restricted to diffusion-dominated regime. So again, in order to overcome this restriction, we draw inspiration from the finite element procedure that we spoke above, and we apply an online control on the high frequencies component of the advection derivative, as described originally in this paper. So in order to briefly describe this approach, so consider that we have a POD projection space like this, which is defined by POD modes associated now to the advection correlation matrix. So now we apply an L2 orthogonal projection onto this projection space by calling it PR, and PR prime is the corresponding fluctuation operator. So we arrive finally at the streamline derivative POD ROM that we are going to propose. And also we further improve this strategy in order to deal with strongly advection-dominated regime by considering a posteriori stabilization. So in order to describe it in a general framework, we can consider like an elliptic variational problem like this, and then a family of finite dimensional subspaces where we are going to apply the Galerkin method for this problem. So if we divide actually the global space X and the solution in this way, and we apply the static condensation operator for the form generated by the form B, we arrive at a variational problem just for the unknown Y, that is the condensed variational formulation described here, where A star is the adjoint of the operator A, defined like this. So in this framework, we can define the so-called saturation property, which can be seen actually as an inverse triangular inequality, and is equivalent to these estimates, and it can be reinterpreted in the sense that the angle between the decomposition space Y and Z is uniformly bounded from below by a positive angle. So we have these results, and we may take advantage of it in order to have a posteriori stabilization of advection-dominated advection-diffusion reaction equations. Indeed, imagine that X is your space, and by Y we denote the large scale, or commonly called the low frequencies component of the space X. So if we are in the offline phase, we can think on X as a finite element space defined on a mesh with grid size H, and so Y is a finite element space defined on a coarser mesh with grid size 2H. While if we are in the online phase, we can think on X as the POD space, and on Y as a subspace formed by a truncated set of POD basis functions. And in any case, that denote the small scale or high frequencies component of X. So my intention here is to show the effectivity of this combined strategy, that is projection-based stabilization together with a posteriori stabilization in the ROM framework. So as space discretization, we are going to consider P2 finite element on relatively coarse uniform grids, where the grid size is much coarser than the width of the internal layers. Both offline and online, we consider a backward Euler time stepping. So here you have the working expression for the stabilization coefficient that are designed by an asymptotic scaling arguments in the framework of stabilized method. And we are going to run all the numerical experiments using FreeFEM. And all detail are, you can find all detail of simulation in this paper published in the framework of the ARIA project. So first of all, I'm going to consider a 2D rotating cylinder defining the unit disk. So you have here the problem is the advection-diffusion-reaction equation with this data. So you have this cylinder that starts to rotate counterclockwise. And after full revolution, due to the very low diffusion coefficient, the solution should be almost the same as the initial condition. So the initial conditions show a sharp internal layer, and we are thus in the under-resolved regime. And since we have a very low diffusion coefficient, we are facing a strongly advection-dominated problem, so that we need basically both offline and online stabilization procedure. And as described before, we are going to compare the use of the stabilizing post-processing both in the offline phase and the online phase. So as quantity of interest, we consider var T, which is a measure for under and overshoots, whose optimal values is equal to 1. So we start with the offline phase. So we first compute just one full turn of the cylinder, and here in the figure you can see the temporal evolution of var T computed by the LPS finite element method, both with or without post-processing. Okay, so you can see that the application of the post-processing is slightly superior to the no application of it, and also you can see the reduce of the oscillation for this quantity when applied the post-processing strategy to the stabilization finite element method. So for the online phase, we are going to save every 10 LPS FEM post solution snapshots in the same time interval where we where we compute the snapshots. So for the POD modes generation, we consider the method snapshots in L2. And here is the decay of POD eigenvalues, both for the snapshot correlation matrix in blue and the advection correlation matrix in red. So for the online phase, we are going to compare the solution of both the streamline derivative reduced order model with or without post-processing. So you can see that even if the first 30 modes already capture more than 99% of the system kinetic energy, here we have that the results are not so good for 30 modes for both methods, since the value approached by T is like 1.3, then this value decrease and approach values of 1.1 after one full term. And you can see also as the application of the post-processing helps to obtain more stable and accurate solution. However, this difference is going to become smaller when we augment the number of when we improve the number of POD modes as expected. And so here you can see qualitatively the final solution of the streamline derivative POD ROM with online stabilizing post-processing. Here is for 30 modes, 60 modes, and 90 modes. And so you can see that numerical and physical oscillation for are almost reduced and limited by applying this kind of strategy. So we are also interested in seeing the long-time behavior of the spurious oscillation. So now we compute for the cylinder 5 full turn around the unit disk. And here again, you can see the comparison between the LPS-FEM with or without post-processing. And as the solution of post-processing is more stable and accurate. Yeah, we are going now to save the snapshot just for the last full turn, since we are interested in the evolution in the stable response regime. And here you have again the decay as before of the POD eigenvalues. And you can see that right now, just with 30 modes, we are able to obtain quite good results for the SD-ROM, both with or without post-processing. And now the post-processing gives slightly better results in a time window which is five times larger than the POD time window used for the basis generation. So for the 2D traveling wave problem, so we have a sharp internal layer moving in time in this case, and also here the diffusion coefficient is very low. Here we can compare with an exact solution, which is this one. So again, we are in the strongly advection-dominated regime. We are going to apply an offline-online stabilization procedure as we described before. And as quantity of interest, we are going to consider the deviation for the final solution profile along the mean diagonal described here. So you can see that in the offline phase, we perform a comparison between a direct numerical simulation in which we not apply at all the stabilization procedure, the DNS together with post-processing, and finally the LPS-FEM with or without post-processing. So you can see how the local projection stabilization is better than a simple DNS, and also the application of the post-processing strategy is able to reduce the error from a 12% to a 4%. So here you can see that the decay now of POD eigenvalues is quite low. So this indicates that the problem is quite complicated and more complicated than the one we considered before. And you can see by considering the first 30 modes for the online phase as all solutions. So the simple Galerkin ROM solution and the streamline derivative ROM solution with or without post-processing almost show a global spurious oscillation in all the domain. However, for the SD-ROM with post-processing, these oscillations are reduced by augmenting the number of POD modes and almost eliminated when we arrive at 90 modes for the SD-ROM with post-processing. So, you get basically error levels that are almost similar to the one of the full order models. So here you can see the final solution for the streamlined POD-ROM proposed with online stabilizing post-processing. So you can see here the solution for 30 modes, 60, and 90 modes. And so again, we can see how the numerical and physical oscillation are almost eliminated by this combined strategy. So to conclude, we can say that in the ROM framework, the combination of a projection-based stabilization together with a stabilizing post-processing strategy allow to attain accurate and efficient solution for strongly advection-dominated regime. Also, we show the robustness for long-time integration quasi-periodic system. And we remember that we applied the stabilizing post-processing strategy in the offline phase in order to limit the influence of POD noisy modes used then in the online phase. And in the online phase, we use it in order to compute in an efficient way more stable and accurate solution. So, you know, in this kind of problem, actually, you always have this kind of numerical oscillation. So one can think, for instance, to apply more complex shock or discontinuity gap-Turing method adapted to the POD-ROM framework in order to further limit the influence of them. And also we can extend and do a similar numerical investigation for the more complex Navier-Stokes equation in order to apply this strategy to convection-dominated and turbulent flow. So here you have a short list of some actual references related to the talk, and that's all. And thank you for your kind attention.
Okay, Samuele, thank you very much for this nice talk. Well, Traian, I think, has some question. Please, Traian.
Sure, thank you. I have a quick question, Samuel. Very nice talk. Thank you. My question for you is, so you mentioned that you do this offline stabilization and online stabilization. Yeah. So can you comment a little bit of what happens if you just use the offline stabilization? Does it work, or does it break down, or when does it break down?
Okay, so you can see here actually, you can see here we perform actually a comparison for the second test of the 2D traveling wave, in which in the online phase we just use we perform a comparison by just using a Galerkin ROM. So here you have the application. The snapshots are constructed with an offline stabilization, but then in the online phase we perform a comparison between a standard Galerkin ROM and the streamlined derivative ROM. And you can see here how the standard Galerkin ROM, even for 90 modes, continue to be very unstable in the world domain.
Thank you.
Okay.
Okay, thank you, Traian. Hi, Sam. I think Sam Telib.
Yeah.
Thank you, Thomas. But actually, it was related to Traian's question.
Okay.
Okay. Good. Are there any other questions?
Can I have a quick question, Thomas? Thanks. So, Samuel, could you be so kind to explain me again in which respect it is the scheme is online and offline? So the stabilization is online and offline. So just the key, I missed the key point.
Okay, so here you can see, I think. yeah, so basically, this is the scheme that we use in order to compute the snapshots. So in the offline phase, we use a local projection stabilization by interpolation by adding basically this this term, which is able to control the high frequencies component of the advective derivative. And then in the online phase, we propose a similar strategy, but now there is no interpolation operator. There is a projection operator that actually acts on a POD projection space. So that are the POD, which is formed by the POD modes associated to the advection correlation matrix. So this one is the online phase. So this is how the stabilizing strategy works offline and online. And then both offline and online, we apply we further apply a post-processing strategy, which basically consists on this. When we are offline, we are going to project the solution onto a coarser finite element space in order to have a smoother solution, basically. And in the online phase, we truncate the solution by choosing less POD modes.
Okay, so great. Now it's much more clear for me.
Okay.
Thanks.
Thank you.
Okay. Any other question? Okay, so I have just a small one. Is about how to optimize the procedure, because of course the stabilization is strongly dependent on the number of modes you choose to project. But
yeah, so
well, how to optimize that?
Yeah, so in the online phase, you can choose like an on the fly procedure. That is, you can try to minimize, for instance, the error in certain norm between the ROM solution and the snapshots whenever they are available, in order to optimize the error that you are doing when you truncate the ROM solution, basically.
Okay. Thank you very much, Samuele.